So this is AP Stats Notes 11.2, Part 2, and this is the final of our 3 chi-squared tests. This one is for the test of independence. This is going to look for seeing if 2 different variables in the same population might somehow or another be related to each other. So it's just looking for patterns and connections between 2 different categories. So it's not 2 different populations, it's not M&Ms from 5 years ago to today. It's one single scoop, but we're evaluating 2 different things. So if it was the M&Ms, it might be color and maybe weight, or color and the numbers of M&Ms that had the little M printed on it perfectly or something like that, right? So 2 related things to 1 sample. So the one we're going to do today is, I went and I looked at what days of the week your birthdays fell on. And I took a random sample of 200 Hart students, and I filled in the data and I filled in the table. And then I went and looked, because I have this magical ability to tell that whether these 200 people were right or left-handed. So in that same scoop, I'm looking to figure out what day of the week they were born on and if they're right or left-handed. Now, obviously this is made up data, right? Actually, some of the days of the week is correct as far as its proportions go, but the right and the left-handed I made up, okay? So we've got one big scoop, 200 Hart High School students, and we're evaluating 2 things to see if there's a connection. Day of the week they were born and whether it depends on their right or left-handed. Wouldn't it be cool if you found out that people that were born on Fridays tended to be more left-handed than some other day? That'd be kind of cool, right? So that's what we're testing for. It's going to run just like the one we just did before this, which was the one for homogeneity. It's just the HO and the HA changed slightly. Now the HO is that the 2 variables are independent, or there's no association between those 2 items, or that they're not independent, that there is an association. It doesn't matter which one of those words you use, just once you pick one, stick to it. All right, so we're going to have the same problem again, where we're going to want to plug this into our calculator and get it started. We're also going to have to do an expected count. So again, I left a couple of those open just so that we could practice with them. So if I wanted to know what goes into this first square right here, how to calculate it, right? We're going to go up to our observed counts. We're going to take the row it came from, 143. We're going to multiply it from the column it came from, 43, and we're going to divide it by the grand total, 200. So if I grab my calculator and I do just that part, 143 times 43 divided by 200. This would be an expected count of, we would have expected to have 30.745. So we're not far off there to what we actually observed, pretty close. Remember that observed have to be whole numbers, expected counts do not. Okay, so you can see that the rest of them are doing all the same thing. They're using that same row, 143, and then they're using the different columns for each one. All right, so let's go ahead and put this one into our calculator, and we'll write up a significance test for this one as well. So this entire chapter, there are no confidence intervals, and 2 of the significance tests look almost the same except for what you write for the null and alternative hypothesis. So quick review, we're going to go into matrix. I'm going to go ahead and edit that first one. I don't need to clear out the one from B. When I run the test, it will replace it for me. Okay, so you don't have to clear out the other one where your expected counts are going to go. I'm going to go and edit this one, the first one, and now I know there are 7 days of the week, so I need to change the 6 to a 7. Okay, so I'm going to change that to a 7, and I'm going to fill in all of the observed counts. So 31, 12, 11, 27, 37, 14, 11, and it goes down to the next row. So 12, 7, 3 7s in a row. Very suspicious. 10, 2 7s in a row. Cool. All right. So again, once it's in here, I'm just quitting out. I'm going to go and run my chi-squared test. Again, you only do goodness of fit when it's that first one, when you're just doing lists. So we're going to go to a chi-squared test. Same deal. My original is in A. I want my expected to be in B. So I'm going to go ahead and calculate it. And this time I'm going to get a 5.05 and a probability of about 54% and a degree of freedom of 6. So let's go through it and see. All right, so our null hypothesis is that there is no association between those things. They have nothing to do with each other. Our alternative is that there is some relationship, that people who are born on Mondays really do have higher proportion of left-handed kids born on Mondays. Okay, all right, so we go through the same thing again. Is it random? It is random. It didn't come from 2 independent samples. The data came from 1 random sample of 200 students. Okay, 10% rule. We are sampling without replacement. This time we sampled 200 Hart students. And if I do the 10% part, we have just barely over 2,000. I think we're around 2,100 right now, so we're still good there. The expected counts must all be at least 5. And looking at all of my expected counts, looks like my lowest are 5.13. So we're okay there. Okay, and again, I'm going to tell them to go look at the expected counts up in its original table. So this is going to be a chi-squared test, not for homogeneity. This one is going to be, what words did I use? I use association. So I'm going to call this one association. And you could use independence as well, but then your HO and your HA should switch to words that relate to independent. Okay. All right, same counts as before here, where we do chi-squared as observed minus expected, square it over expected. And in our original ones, we had a 31 in the first spot, a 30.745, right? And I'm going to, again, keep doing that until I at least set up 3 in a row, and then I'm going to show all the way to the last one on the last row. That's this one right here. And we set on our calculator that is 5.05164, something like that. So we're looking for 5.052. So I'd be doing chi-squared CDF from 5.052 to infinity, and a degree of freedom is 6. Now, how do I know that this time? So this time we had 6 in a row. We had 2 rows, and our columns were 7, right? Days of the week, 7. So that's going to be 1 times 6. That's a degree of freedom of 6. Here is our picture. And again, if you needed to see the picture, you could go back, run the test, have it display so that you know what shape you're drawing, right? Because sometimes the shape changes a little bit, especially when the degree of freedom is smaller. So if you're not sure what to draw, just choose the draw option. And there we go. It's going to look something like that. So I'm just basically copying this one, it goes up like this and then goes down for a very long time. And I'm picking it to be right about there, 5.052. And this one is a chi-squared distribution with degree of freedom equals to 6. Okay, so I'd say chi-squared equals. Cool. All right, so we know our probability for this one is 0.537-ish. And again, I'm going to go back and rerun it the other way just to make sure. I thought the probability was slightly different. Let's go see. Maybe I'm thinking of the last problem we did. 5.37, okay, cool. Okay, so because our p-value was 0.537, which is more than any reasonable alpha level, we would fail to reject HO, which means we do not have convincing evidence to conclude that there is an association. Remember, this was our HA. So we don't have proof that there's an association. No shocker, right? And it probably has nothing to do with what day of the week you were born and whether you're a right-handed or a left-handed person. Cool. So that's our last chi-squared test. That's it for chapter 11. It's just knowing those 3 types. So I've given you the examples kind of that we've used here a little bit at the bottom to know what the differences are between the 3 tests. Okay. So the first one is the birthdays that we just did. Okay. So if we wanted to know if they were evenly distributed, that would be like the M&Ms one where we would say just take 100% divided into 7 equal days. And those 200 people divided by 7, how many would be in each day? And just evenly distribute them, that's your expected count. Okay, homogeneity would be maybe if I said, are the distribution of birthdays the same for Hart High School as it is for Valencia? Maybe there's a difference there. So again, that would be 2 populations that I'm comparing. And association would be, I wonder if the birthday and the handedness are associated at all. Okay, back to our M&Ms example. If we're just looking for the color distributions from their stated, that's a goodness of fit. Homogeneity would be if I'm comparing 2 different populations. I wonder if the distributions are the same from 5 years ago. An association would be something else other than color in that same sample. So the weights or the numbers that show the complete M on the candy or something like that. Is there an association between what color it is versus what the weight of that candy is? Maybe some of the dyes are heavier than the others, something like that. Cool, so you should be able to name them correctly. It's not good enough to just call it a chi-squared. You're going to actually have to say which one of those three categories it is. And we give you some hints at the very first page of not these notes, but the ones from, where did they go? Like here. Okay, so remember up here at the top of yesterday's notes, we had all of the different tests and the test for independence and the keywords that you're looking for. So for example, we were saying that for homogeneity, you're looking for sameness or differences. For independence, we're looking for a relationship between or a correlation between two things. And then our favorite goodness of fit is something about matching it to something else. Okay? I think goodness of fit is one of the easiest ones to tell because it's only going to have one row in the entire distribution. So it's pretty easy to spot. It's the differences between homogeneity and association that take you a little bit of time to figure out, am I grabbing from two different populations? That's probably homogeneity. If it's one sample and they've just created a new category, color and something else, that's probably association. I hope that helps. Bye.